So the fission process begins with a collision of a high-speed neutron with a large unstable nuclei. These are like radium or uranium-235, plutonium-294. The unstable nucleus splits into two medium-sized nuclei like barium or krypton, and then most importantly, three more neutrons are released. It's these three neutrons that can then go on and split even more nuclei. Those nuclei also release three neutrons, and ultimately what we end up with is a huge number of neutrons flying around, splitting a huge number of nuclei, and this is called a chain reaction. And this is sort of a schematic diagram of the single neutron splits the nucleus, produces three neutrons. Those neutrons go on to split even more. Now let's take a quick look at two short videos that sort of illustrate how this process works. So we bring in the neutron splits the nucleus, we release three neutrons on the right side. Those two neutrons then go on to split other nuclei. Those nuclei now release three more neutrons. Those neutrons can now split even more nuclei, and you see that very rapidly we can split a lot of nuclei. Here's an even better video. This one shows the uranium-235 nucleus with all of its protons and neutrons, but also shows the electrons buzzing around. Now here comes our high-speed neutron. You can see other nuclei in the background. So temporarily it fuses. The nucleus, I should say, splits into two parts. This is the example from the book. Here's the barium and the krypton, but then also the three neutrons. Those three neutrons then fly outward, striking three more nuclei. Those nuclei split. Now we have 9 neutrons. They hit 9 more nuclei. Now we have 27 neutrons, and you can see very rapidly that we end up with a large reaction. Now here's an interesting way of representing the chain reaction using mousetraps and ping pong balls. So in this case, the mousetrap represents the atom, and the neutron represents is represented by the ping pong ball, I should say. We bring in one more neutron represented by the ping pong ball. It initiates one fission. That fission causes more fission, and you can see that slowly over time all of the atoms, which are the mousetraps again, undergo the fission process. Now here's an even bigger demonstration of this.
Electric co-ops don't just generate power. They generate ideas. We also share them. At your Touchstone Energy Cooperative, we never stop thinking of ways to help everyone be more energy efficient. New technologies to improve reliability. Opportunities that can benefit us all. We know a single idea can spark hundreds. With all those ideas coming into contact, we can create solutions to whatever challenges come our way.
So I think that demonstrates pretty successfully the chain reaction process. Now, we use this in two ways. First, in nuclear power plants, we actually use moderators that absorb some of the neutrons and slow down the reaction. And this allows us to control the reaction and release the energy very slowly, which we then turn into electricity. Of course, the most famous power plant in America is the one in Springfield, but actually nuclear power plants are very common. There are more than 110 nuclear power plants in the United States, although there have not been any new power plants in almost 30 years because of regulation problems. Now, there have been problems with power plants. In 3 Mile Island, this is in New Jersey, the two power plants in the upper right, they had a partial meltdown, and as a result of the partial meltdown, you can see that they've actually disassembled part of the cooling towers in the upper right-hand corner. Now, we've only had a partial meltdown. Fortunately, nobody was injured, but in Chernobyl, this is in the Ukraine, formerly the Soviet Union, they had a complete meltdown. They lost complete control of the core. The core reached more than 5,000 degrees and melted its way outside of the containment chamber, where it then exploded and released toxic nuclear material into the air. Now, on the other hand, we could have what we do with our nuclear weapons, in which case, instead of controlling it, we actually let it go completely out of control. We have a very concentrated supply of the fissionable atoms, and once we start the process, we release all of the energy very quickly, extremely suddenly, in a split second, and this causes, of course, devastating results. The temperature, when the nuclear reaction starts, is at 10 million degrees Celsius. This is equivalent to the core of the sun. That's 18 million degrees Fahrenheit. And we've only used these weapons a few times. One of the first ones that we used is up in the upper left-hand corner. This one was called Fat Man. That was used on Nagasaki in Japan in 1945. It had the equivalent explosive power of 20,000 tons of dynamite. 20,000 tons of dynamite. And the characteristic mushroom cloud is what people think of when they think of the nuclear explosion. Today, actually, we don't use nuclear weapons. Our more powerful weapons are called fusion weapons, and we're going to look at that in the next chapter. but nuclear weapons have become quite common. The material to produce them is actually not that difficult to get a hold of. You simply need a certain amount of that material, a certain concentration of it, and when you achieve what's called the critical mass, then you're able to create the nuclear weapon.